next up, moving on to our next session, number 6, with our data hero, Lenny Fishler, who's head of data services at Braze. He's based in New York City and established the data professional services team at Braze. He is another one of our local user group leaders, in this case in New York City. And he's going to talk to us now about how Snowflake with Mongo ChangeStreams can drive near real-time business intelligence insights. So, okay, Sonny, take it away, man.
Hey, Ken, thanks for that intro. So yeah, as Ken mentioned, we're going to discuss how to use Mongo and how to stream those Mongo changes into Snowflake, and then how to work with those changes. So let me know if you're seeing my screen and if you're seeing the slide switch.
Yes, we're seeing your screen. That's great.
Great. So I'm looking at another screen, so I'll be looking up the whole time. But feel free to ask any questions, and then there'll be a kind of a small Q&A towards the end as well. So as Ken mentioned, we're going to discuss how Mongo ChangeStreams help us drive real-time business insights, and how Snowflake comes in handy as like a key tool to make this whole operation work. Just a brief agenda. First, I want to intro everyone here to Braze and what Braze does. Then I want to kind of switch gears towards a business problem that we had that inspired us to write this architecture. We're going to move into Mongo ChangeStreams and what that really means, and how that works for those not familiar with Mongo or not familiar with the change streams themselves. And then we'll dive into the fun Snowflake part, where we're going to use Snowpipe, tasks, and streams to put it all together. So without further ado, so quick intro to Braze.
Hey, Lenny, your slides are not changing.
Okay, let me do one mod here. Let's try this. How about now?
All right, it's on your opening slide. Yep, changed. Perfect.
Great. So quick intro to Braze. Braze is a customer engagement platform. And what that means is that we connect brands such as Domino's here or Lyft to the end users or the customers. And we do that through sending various messaging campaigns, segmenting audiences, and then kind of sending that data back after measuring performance into Braze to optimize campaign sending and to really personalize the experience of the end user. So anytime you receive a Lyft email, that comes from Braze. Anytime your Domino's pizza is on the way and that personal experience that you get, Braze powers a lot of that infrastructure, in addition to a lot of other brands here. And the way we do this, the way we again connect the brands to their end users or their customers is through push email, in-app messages, and other kind of marketing campaigns. We have integrations via SDK as well as REST API, and we strive and pride ourselves in real-time audience segmentation. What that means is that at any point, at any point you may perform some action which may put you in a different segment or remove you from a segment, and Braze handles that in a dynamic fashion. We use batch, event-driven, and transactional API messaging. And as you could probably tell, all these campaigns sending to end users on a large scale generates a whole lot of data, right? So we have 11 billion user profiles, 8 billion Sidekick jobs, 6 billion API calls, and over 350 MongoDB operations across all our clusters. And this slide is not completely up to date, so these numbers have grown since I put this together even. We use Mongo as our main store of this data. But as you may know, Mongo is not great for analytics. It's great for, having this fast performance, fast transactions, but for analytics, it's not great. And I'll tell you why, or a few why. First, we have sharded Mongo across regions and across our own clusters. So it's hard to do joins, or as Mongo calls these things, lookups. So as you could probably tell, without doing joins, it's really hard to do any analytics. And that's not even to mention grouping by something that you join on. Mongo is also notoriously hard to query. So you have to either write aggregation pipelines via, JavaScript, some kind of a connector, or a MapReduce job, which inherently is abstract and also time consuming. So, we've got into situations where our MapReduces have slowed us down a lot. So in the end of the day, we'd rather have Mongo be that kind of big booster in terms of our customer experience, and then use another platform. So we need to get that data exported to do the deep analysis that is extremely hard to get to and extremely hard to do in Mongo. So how do we do this, right? One way is to make full copies of Mongo data, load it into Snowflake, and then either use Snowflake or another BI tool to analyze this data. But that's not great, right? Making full copies of data, whether it's on a weekly basis or on a daily basis, incurs storage costs, compute costs, both in Snowflake, AWS, our own infrastructure, and it's just costly in the end of the day, right? And in the end of the day, as a business, we want to make sure that we don't run over our costs and make customers pay less rather than more if we can. So also, if you export data and full copies of data, you could do this once a week or once a day. Nevertheless, it's not up to date, which slows down analytics and doesn't let you do real-time business intelligence and real-time insights because of this once a day or once a week paradigm. So clearly there must be a better or a more elegant solution. And that comes with a feature called Mongo ChangeStreams together with Snowflake. So just wanted to go over the overall architecture. So here's a sketch of how it all works, right? And there's a lot of moving pieces here. There's Mongo pieces, Snowflake pieces, and I think it'd be best to just break this whole thing down into each individual component, and then we'll put it all together in kind of a logical, cohesive fashion. So breaking it all down, first I want to cover Mongo ChangeStreams. So you may be asking, what are Mongo ChangeStreams? So first and foremost, Mongo operates with collections. So a collection is pretty equivalent to what a table in Snowflake is. And each collection has documents, and a document could represent a campaign or a user. So these collections change all the time, right? There may be records deleted, updated, new records created, etc. So these change streams capture these changes, and they allow applications access to these real-time changes without much complexity, such as tailing a log and grepping a log or processing a log in a way. So it's pretty much makes capturing of these changes easier to work with. And then applications can use these and subscribe to a specific collection, a specific type of change, or multiple collections. So what we do at Braze, we subscribe to multiple collections, change streams. Those collections or those tables power our analytics. So moving on, what exactly does a change stream look like? A change stream, again, is a JSON document, and Mongo operates in in this paradigm called BSON, which for the simplicity of this presentation, let's just think of this as a JSON object. And it has a few parameters, but I want us to focus on the 3 parameters that are of most importance to this architecture. First, it's the ID of the change. And we want to capture that ID to make sure we identify that that is indeed the change that we processed in every step of our pipeline. Then we need the operation type. So what kind of change occurred in this collection? So this could be an insert, delete, replace, drop, rename, drop database, invalidate. The ones that we focus on are insert, delete, replace, and update. Drop, rename, and drop database and invalidate, we don't really use very often, and those have their own kind of downstream pipeline. But in terms of changes into Snowflake, it makes a lot of sense to just use the top 4 here, as well as the full document. So this is the new updated full row or full document in a specific collection or in a specific table, as it will stand in Snowflake. So moving on, now that we understand that change streams are basically a way to capture changes in our Mongo collections, we want to capture these changes, store them into files, and then batch them into Snowflake. That's the goal here. So how do we do this? We use an Amazon EC2 instance. This is just a compute instance in the cloud to capture these changes. We batch them 10 events, and then we create a file that has those 10 events. Then we wait for 10 more, batch them, create a file, we have another file. And each one of these files, as they get created, they get synced to the S3 bucket. And these files are JSON files. And of course, since they're in S3 and they're in JSON format, Snowflake could easily ingest these files. So now moving on to the fun Snowflake part. So again, we left off in having JSON files that, that have 10 change streams per file in an S3 bucket, and it's now ready for processing in Snowflake. So first and foremost, going over how we ingest these files from S3. So first and foremost, we want a clean copy of the data, of yesterday's data, so to say, right? Of data at T0, basically an up-to-date copy that has not captured the changes that happened. So we clone a copy of the data only once, right? We're not doing this daily or weekly. We only need to do this once ever. So that's a huge, huge win here. And then we create auto ingest snowpipes and create another table that has 3 columns. And the 3 columns are, again, ID, the document, and the operation type. So what is the change that happened in the document along with the ID of the change. And then, of course, these auto ingest pipes ingest into a new table. So let's take users as an example. We have a clone of all our users called user clone. We create a new table called users, and we ingest into this table these 3 columns from our S3 bucket that, if you recall, has 10 changes, and then there are more and more files created. And auto ingest pipes, of course, as soon as a new file gets created, we will ingest it into the new table. So now we have, again, a users clone table that has yesterday's data, and a users table that just has the changes, new changes, after that clone has been performed. So then we take advantage of Snowflake streams and tasks to process this users table. So we create a stream on the users table, and again, the users table has all our changes, and we call this users stream, for example. And from there, again, the stream captures any new rows in this table, and every row represents a change. So then we create 3 tasks because there are only 3 real operations that we need to do on the yesterday's copy, aka user's clone. So the 3 tasks here is a delete task, and the syntax is here. It of course ingests the operation type, which is delete, and then the metadata action, and this is the metadata action of the stream, is the insert here. So it inserts into the table. So actually there is a small typo here. The metadata action in delete should be delete. So just a small clarity, and I'll change that before sharing this deck. So yeah, there's 3 tasks. Delete task that deletes rows from the user's clone table. There's the insert task that inserts into this user's clone table, where operation type, remember we captured that operation type from Mongo, is insert, and the metadata action is also insert. And then the update task, I'm going to leave this as an exercise. If you're curious to recreate this yourself, this is all in a Snowflake documentation, so you could copy kind of an example and then change that on your own. So this is how it looks like from our S3 bucket. Files get ingested into the S3 bucket. They contain all our changes. Then they get snowpiped into the users table. And again, the users table is a new table that has all our changes. And then on that users table, there's a stream. And that stream triggers 3 different tasks: the update task, the insert task, and the delete task. And those tasks indeed change our user's clone table. So our initial copy of the table that we did at time 0 or yesterday. So now I want to ask the audience, and I'll give a couple of minutes to answer this. So what is in this user's clone table now?
We have one answer that says curated data.
That's definitely correct. Any other suggestions?
You can put your answer to Lenny's question right there in the chat, people. Anybody else want to take a shot at it? What is in the user clone table? Data as of current source.
I like that. Yes, I think state as a current state, I would say is but yes, I think it's in the right. It's in the right on the right branch of thought for sure.
Okay. Current state. Incremental data.
Incremental data.
All Mongo changes replicated to the Snowflake table. And then the most recent one, latest representation of source data.
Yes, I think that last one hits it right on the head, and all those above are mostly correct as well. So it's a new table that contains all the latest changes that happen to our original clone, aka the latest state. So then as fast as changes are written, sent to S3 and ingested by auto ingest Snowpipe. So it's as real time as sending data to S3 and auto ingesting it. So pretty near real time. Almost near real time. And lastly, now that we have a user's clone table that has our latest changes, we could do analysis with this, right? Which is kind of the what we're striving to get to, our main business goal here. So now we could get insights quicker, enact them and act on them in a timely fashion, empowering people to see these insights and act on them. And when I say people, both inside of Braze and for our customers and any products that we're spinning off of this. So that pretty much sums up the presentation. Maybe I will leave kind of the architecture slide up so you could see. Let's go back. Sorry. There it is. And then I'll take any questions from the audience.
All right. Well, first question, what is the average latency?
So it depends on the Mongo collection. So certain collections have changes happening all the time, right? We have collections such as event collections that change every second. So those have more latency, and then other ones that don't change as much, they happen to have less latency. But it's hard to estimate an average. I would say around anywhere from 0 to 5 seconds.
Okay. So does Snowflake then have all the historical changes with this approach?
So by historical, I'm assuming, so because we started the clone at time t0, as you see up top here, Snowflake copy of the Mongo collection at t0, it has everything from t0 and on. So it has the state at t0, which of course has all the changes up to that time, and then all the changes after. So short story, yes, it captures all the changes, but it doesn't have records of all the changes. It only has records of changes from T0 or yesterday and on.
So it's not a full type 2 sort of record of all the transactions that have changed. Right. It's just starting from T0. Like you said, from there forward, you've got all the incremental changes and the current state.
Yep. So to vet kind of the whole process, you could see, you're assuming that T0 is a truth, right? Is a ground truth or a source or a truth source that captured all the changes beforehand, and then you could vet everything from then on. And again, kind of going back to the business goal here, the business goal here is to analyze the table as it stands this second or 5 seconds ago. So we don't need to write all those every single change. I could also see that writing every single change for basically making a copy of the log being also costly both on the compute and the storage.
Okay, so how did you come up with the number 10 for the number of changes per file? Did you play around with this value, and is this what got you the most throughput, lowest latency, whatever? Seems pretty small, even for micro batching.
Yeah, so we want it to be as near real time as possible. Also, Mongo works in its own mysterious ways that just to kind of glance over it, like there are batches that this data needs to come in, et cetera, et cetera. And for the collections that we played around with, 10 seemed like a good number that didn't cause much failover. Many, Mongo reconnection errors, or like Mongo has this mystery cursor, so to say, basically didn't have any cursor errors or retry errors, and that number worked well. And also we want to make this as real time as possible. And if the Snowflake auto ingest pipes could ingest all these files very quickly, then 10 is a good number. That way, we are getting those changes, as I mentioned, in real time or near real time.
And that actually, I think, answers another question. There was a question on the chat that said, is the size of 10 configurable. And sounds like it is. You picked it and set that number yourself.
It is, and I think as we kind of productize this and as we roll it out across other clusters, this has only been rolled for one of our 10 clusters. We'll potentially change that. This is a kind of a high throughput cluster. I could see that number, being tweakable to 100 or 1,000. But yeah, it's basically a number that we set in our script that we could change later down the road.
Right. Okay. How do we handle document sizes greater than 16 megabytes with Mongo?
I don't think Mongo handles document sizes greater than 16 megabytes.
So you need a different product.
Well, basically, our Mongo transactional architecture doesn't allow us to have more than 16 megabytes in a single file. And basically, we haven't seen a single collection or a single use case from the customers. And we have hundreds of customers. We haven't seen that being an issue. Yeah, so far it hasn't come up. I think when it does come up, we will re-architect upstream. So we just won't let, for example, a user's collection, let's say a user has a million custom attributes or attributes about you. Let's say, for pizza, you bought, a pepperoni pizza and then a plain pizza and then a large pizza and then the 555 deal, et cetera, et cetera. We haven't run into a situation where there's so much data on the user that we need to kind of re-architect that. But when that comes upon, I do see us potentially having another collection. So similarly to what you do with a database where you split it up into a different table and then you would join or you would call that table with a one-to-many relationship, you could do the same with Mongo because, JSON is a key value store. So, for a single key, there could be many values and those values could call other documents.
Yeah, so another interesting question. How do you deal with a change in schema in Mongo if the Mongo table schema changes, the design changes? How do you reflect that in Snowflake?
So right now we don't, we haven't accounted for that, and that would likely cause some changes to tasks and streams. But just kind of want to just bring up the pieces that are the types or the option changes. It would likely call maybe invalidate, or it would be an update. But basically, if it's another row added, then we would just capture that full document, and then we would see that there's a field and there's a column mismatch. So I think that would cause some errors in Snowflake. But yeah, short story is we haven't architected that, but really good point to bring up to make this better.
Okay, well, I'll take the last question I can take here. We're out of time. Will the stream follow the latest record principle as discussed earlier for Mongo ChangeStream 2? So I assume that means will the Snowflake stream follow the latest record principle?
I think it does. And the Snowflake experts could correct me if I'm wrong. Basically, it captures deltas. So the deltas would be a new row. Being added to that new row would trigger the task that's appropriate.
Okay, well, thank you very much for your time, Lenny, and for this presentation. It was very interesting. There are a few other questions still open on the Q&A panel, so if you would head over there and try to answer some of those, I'm sure that the attendees would appreciate that.
Of course. Thank you, Kent, and thank you for all the other heroes.